Hello, and welcome to Aggressive Physics. Today is day 22, our trigonometry review. Now, trigonometry is something we're going to need to use in order to solve vector problems, and ultimately in order to solve projectile motion problems. Any problem that's in two dimensions can have variables that are at angles. Now, trigonometry allows us to solve for anything with angles. And what we're going to use is right triangles in order to do that. Now, a right triangle has two legs and a hypotenuse. The hypotenuse is always longer than the legs of the right triangle, and we can have angles from 0 to 90. Now, if we had an angle of 0, it would be a pretty boring triangle. It would be a flat line going horizontally. You could say, however, though, that the y direction is 0. You could use that if you know that there is a problem that is going to be solved in two dimensions later on. We can have an initial velocity that just goes sideways. Well, that just means that the initial velocity in the y direction is 0. If we have a y variable only, that's a pretty boring triangle also. But it doesn't have any x motion. So you've actually solved a number of problems already that could be defined as projectile motion, but we don't define it as such because it's only moving in one direction at a time. So a vertical problem is just a special case of projectiles that don't go sideways. A horizontal problem is just a special case of a projectile motion that doesn't go vertically. Now the problem is, if we throw something off a table, it will start to move in the vertical direction as well. So we could have solved a problem where we roll something off a table already. Once it enters the air, though, it becomes a projectile. And it's going to have vertical motion once it leaves the table. Now, hopefully at this point, you're okay with the fact that the bullet would land at the same time as the fired bullet if we drop them at the same time. But if not, there are a number of different example problems we can do. We can do problems with rivers. A lot of times, classic physics examples involve boats and rivers. And if I'm in a boat and I'm trying to travel across a river, my across motion, and the current's going to drag me downstream, my across motion will not have anything to do with my sideways motion. The effect will be that I end up downstream, but if I always point my boat directly across the river, then the only variable I'm going to need is the one pointing across the river in order to solve problems across the river. For example, if I want to know how long it takes to get across the river, and I know the distance across, and I know that I'm only pointing my boat across the river the whole time, I could just do v equals d over t with the value that I had for the boat's speed, whatever it reads on the speedometer. Will I go directly across the river? No. I'll end up downstream. But what I can do is utilize that independence of vectors. Since vectors are independent when they're perpendicular, the across motion and the downstream motion are 90 degrees from one another and can be considered independent. Now, back to trigonometry. In math class, many of us learned trig at some point in time. Now, trig has two different pieces that will be useful for us in this course. The first piece is Pythagorean theorem. And in order to find the length of any side of a right triangle, you need to have two pieces of information. You need to have two of the legs, or one of the leg and the hypotenuse. And the equation is simply a squared plus b squared equals c squared. That's what you learned in math class. For our purposes, we might use it as vx and vy to get v total. We may use dx and dy to get d total. But the reality is most of us are comfortable with a squared and b squared, so we can use those as our variables. Just keep in mind, a and b are the legs, c is the hypotenuse. The hypotenuse always needs to be bigger than the legs. So, if we have the legs of the right triangle, a special right triangle of 3, 4, and 5, if we multiply the legs to find the hypotenuse, we would do a squared, which is 3 squared, plus b squared, which is 4 squared, equals c squared. Well, 3 squared is 9, and 4 squared is 16. 9 plus 16 is 25. 25 equals c squared. Take the square root of c, or I'm sorry, take the square root of c and the square root of 25, and end up with 5. So a special right triangle you can use, since many of you already know that, to verify the equation for Pythagorean theorem. On the other hand, we can also determine the angle of a right triangle. And we can use 3 of the trig identities: sine, cosine, or tangent. I learned it as SOHCAHTOA. SOH equals CAHTOA. So, sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. What's important to realize for these 3 equations is that the angle that's touching the line is the adjacent one. So the angle, usually in the horizontal, touches the x-axis. So the adjacent is the x component. The vertical component is the one opposite the angle. So that's usually the y component. And that's when we figure out the angle with respect to horizontal. Now, most of the time, if you're throwing objects, you're throwing them with respect to the ground, a certain angle, or you're kicking a soccer ball or a football. So you're going to use the horizontal angle. That means that 95% of the time, you would use the cosine to determine the x component and the sine to determine the y component. That's even one of the equations on the reference table. Vx equals v cosine theta. Vy equals v sine theta. That's not 100% of the time, so don't get too comfortable with that equation, but most of the time that would be your fallback. Remember, these equations are actually on the reference table in the geometry section. When we did the area and the slope, the areas were actually in the reference table as well. But I didn't mention that because most people are okay with base times height and 1/2 base times height for rectangle and triangle's area. However, a lot of people are more hesitant with trig, so I want you to remember that the security blanket is there. The reference table can help you remember the equations when you're feeling stuck. Now, determining the numbers is one thing. Make sure that you also include the units. When we're dealing with right triangles, we can never combine velocities and displacements. If you have displacement information, that can only be used with other displacement information to get the, let's say, resultant displacement. If you have a problem with velocities, that can only get you velocities. So if you have a problem where you're trying to find displacements and velocities, you actually need to have 2 separate and unique triangles. So you may be doing problems with multiple triangles in order to solve for the final answer. You cannot combine a velocity and displacement in the same triangle. It doesn't work that way. So each triangle needs to have only one unique set of units. And that's why I think it's important to put the units in the triangle so you remember that. You don't want to have meters and meters per second in the same triangle. It doesn't work. Now, the other thing that's important is that we're going to have to deal with the angles and possibly the quadrants that the vectors are in. So I think it's important to talk about the direction of our conventional directions for 2 different coordinate systems. In math class, most people use the XY coordinate system, and we go counterclockwise around the quadrants in order to determine the angles. A circle is from 0 to 360 degrees. So what we're going to be able to do is go all the way around a unit circle from 0 to 360. Now, the rightmost direction in the x-axis is where we call 0 and 360. The vertical is 90. The horizontal to the left is going to be 180. The vertical downward is 270. And the horizontal again to the right, like I said, is 360. So we wrap around in a counterclockwise direction from 0 to 360. So we have a couple of examples, and I'd like you to try to draw 30, 90, 120, 330 degrees, 75 degrees, 240 degrees, 310, and 155 on different coordinate axes. What we'll do is I'll show you those examples in a few moments. But I'd like you to try to figure out where they would be drawn for the different directions. Now remember, you may have used the word quadrants when you did this in math class. Quadrant 1 goes from 0 to 90. Quadrant 2 goes from 90 to 180. Quadrant 3, 180 to 270. And Quadrant 4 from 270 to 360. You also learned rules about what's positive and negative in those quadrants, and we'll talk about that more later. All right, in order to measure the angles, what we're going to need to use is a protractor. And what I have here is a protractor that I printed out. If we take the protractor and measure 30 degrees, we know that the axis for the XY coordinate system goes 0, 90, 180, 270, and then back to 360. So the degrees for each represent the quadrant they're in. So if I want to measure 30 degrees, what I'm going to do is take my protractor, I'm going to line it up with the axis, and I'm going to make a mark where the 30 is. I'm then going to take a straight edge and go from the origin to that point. Origin to that point. And that would be a 30-degree angle right there. 90 degrees is easy because it's along an axis. So I would just trace the axis if I already have it there. 120 is in quadrant 2. And what I can do is I could start like this, line it up with the 0, measure around to 120, starting at 0, meaning I'm reading the inside numbers on this protractor, make a mark, and connect the dot. That would be 120. I can also do the following, measuring from the other side, realizing that if this is 180, I can go backwards to 60, and that's the same location. Now 330 is in the 4th quadrant, and what I'm going to do is I'm going to remember that if this is 360, I'm going to work backwards to get to 330. So 360, 350, 340, 330. And it happens to be a 30-degree angle on my protractor. Go back to the origin and connect the origin to that point. Now, of course, if you're using a pencil or a pen, you're going to have thinner lines, and it's going to be a little easier to do. Plus, I'm looking at an angle, so I may have some parallax error doing this. I can't be directly above it and still film this. So what you'll do is, depending upon the quadrant you're in, use your protractor. And you can hold your protractor like this. I call it frowny face because it's got a frown. Hold it like this. That's your smile. Hold it like this. Person standing looking to the right. That's your belly. Hold it like this. That would be butt style. So you have frown, smile, belly, and butt. Sorry to be so frank. All right, let's look at these sample problems. 75 is in quadrant 1. So I'm going to hold it frown style. I'm going to measure up to 75, make my dot, and then connect the origin to the dot. 240. Well, that's past 180. And if I do 240, I could either go 30 less than 270, or I can go 60 past 180. I'm going to opt to do 60 past 180. And you'll notice that that's the same spot either way. So 10, 20, 30 that way, or 10, 20, 30, 40, 50, 60 that way. 240 will look like this. 310 is in the 4th quadrant. What I'm going to do is I'm going to hold it belly style this time. And I'm going to realize that this is 270, 280, 290, 300, 310, which represents 40. I'm going to draw my line like this. Ooh, not as straight as it could be. And then finally, 155, we could actually use the protractor in its entirety if you hold it frown style, start at 0 and go all the way to 155, to be just about there. Like I said, if you have a pencil, it's going to be a smaller line. It's going to be a little easier to draw. and you'll have less, well, you won't wipe the lines out like I'm doing. So those are 4 examples for 75, 240, 310, and 155. And with the XY coordinate system, we measure all the way from 0 each time. So that's where we're measuring from. And those angles, this 310 almost wraps around back to 0. On the other hand, many problems in physics are going to deal with real-world problems. So we're going to use a real coordinate system that represents the map on the globe. And we use the north, south, east, west coordinate system. Now, north, south, east, and west, the north is vertical, south is vertical in the downward direction, east is horizontal to the right, and west is horizontal to the left. Now, you may have used mnemonics to determine that. Never eat soggy watermelons. You go clockwise around. North is never. Eat is east. Soggy is south. Watermelons is west. Or you may have learned different mnemonics to determine the coordinate axis for north, south, east, and west. The compass directions are standardized, and we use north, south, east, west always in the same direction. Now, if you're going north, it's easy. You're just going up. South, it's easy. You're going south. East to the right, west to the left. But sometimes you're dealing with an angle at a certain degree. Northeast, southwest, southeast, or northwest. Those would be at 45 degrees, and that's a default. But you can also go at any angle between 0 and 90 for each. We always use acute angles for north, south, east, west, and you're going to that means that you're going to go from 0 to 90. So you may have an angle of 30 degrees north of east. You can also have an angle of 30 degrees east of north. Now, although the 30 is the same and the 2 directions are the same, it actually represents 2 different values. 30 degrees north of east means it moves up from the east 30 degrees towards the northern direction. 30 degrees east of north means you're going from the north 30 degrees over to the east. If you wanted to replace that angle with something else, you could actually say 60 degrees north of east, and that would be the same as 30 degrees east of north. This gets a little confusing for students, so what I'd like to do is a couple of example problems. But remember, it's always going to be a direction of another direction. And you're always going to have blank of blank. For example, north of east. Now, the way I remember this is my second one is always where I started with my protractor, and the first name is where I turn towards. So if I'm going 30 degrees up from east towards the northern direction, I'm going to go 30 degrees north of east. If I have my protractor on the north axis already and I turn to the east, that's going to represent 30 degrees east of north. So let's try to draw a couple of examples, and then I'll show you those examples on the whiteboard. So let's try these example problems. 30 degrees north of west, 15 degrees east of north, 70 degrees south of east, 60 degrees south of west, 25 degrees west of south, and then finally 10 degrees west of north. Each of these will represent different directions on the coordinate axis. We're going to be able to use those to find the legs of the right triangle in future problems. But remember, perpendicular vectors are independent. Trigonometry, although scary in math class, is going to allow us to solve seemingly complex problems. Well, they are complex, seemingly impossible problems quite easily. But we need to remember the basics. SOHCAHTOA and a squared plus b squared equals c squared. Now let's get on to some of those sample problems. Okay, now we're looking at the the north, south, east, west coordinate system. And what's specific about that is we're always going to measure 90 degrees or less. And we have north, south, east, and west. Never eat soggy watermelons. And what you're going to do is always hold the 0 line along the axis of the second letter. So I'm always going to focus on the second letter first, which is a little counterintuitive. but that's the easiest way that I've found to do this. If you come up with a better method and it works for you, that's fine as well. But if you go to that western point, which is that second letter there, we're going to go 30 degrees up towards the north. So I'm going to go 10, 20, 30 degrees upward. And this angle here would represent 30 degrees north of west. Now we can also write the complement of this, and that would be this angle. Now if this is 30, this angle has to be 60. But we can't say 60 degrees north of west. What we have to do to measure 60, we would have held this along the northern axis and turned to the west. So this second one is actually 60 degrees west of north. So the same location can have a complementary set of directions, in this case 30 degrees north of west or 60 degrees west of north. And we always put our 0 line along the axis of the second letter. So let's do the same with east of north. All right, this is going to go, well, we're going to go to the east. So we're going to hold it this way, belly style. And it looks like I'm going to write on top of my of. All right, about there. Kind of see where I made that mark. And draw my line in that direction. Okay, it points to that dot that I made in the F. 15 degrees east of north. The complement would be 75 degrees north of east. And that way I would hold the protractor on the east and go up 75 degrees. All right, 70 degrees south of east. I'm going to hold it smile style. I'm going to start at the east, and I'm going to go down 70 degrees to the south. Mark it there, and connect my dots. There's 70 degrees south of east, this one. The alternative would be 20 degrees east of south. So those are those three examples. And let's do 3 more. Okay, we have 60 degrees south of west. So I'm going to hold the protractor along the western side, which is over here. And I'm going to go 60 degrees to the south. I'm reading the inside set of numbers on mine. Make a dot. And connect the origin to the dot. South of west. 25 degrees west of south. I'm going to hold it butt style. I'm going to go 10, 20, 5 to the west from the southern axis. I measured there. For the 60, I measured here. And then finally, 10 degrees west of north. Also butt style. 10 degrees, not a very big angle. Make a mark. And draw it like that. This was 10, which means that would be 80 degrees. Now 80 degrees will be written as north of west. So you have different options for different measurements. And it's important to hold the protractor along the second direction of each of the blank of blanks. All right, let's look at some trigonometry problems. And what we have are a few equations that we can use in order to calculate either the legs of the triangle, the hypotenuse, or the angle. The right angle, I use this symbol here to represent the right angle for each. And what I did is I tried to draw 2 different triangles in different orientations, because it seems like a lot of times we're stuck with this single orientation where the right angle has to be on the horizontal. It could be at the top part of a triangle. It depends on the situation. Now the equations are the Pythagorean theorem, which is typically a squared plus b squared equals c squared. And we also have sine theta equals opposite over hypotenuse, cosine theta, which is adjacent over hypotenuse, and then tangent theta, which is opposite over adjacent. Now the way this works is the one leg that touches the angle is known as adjacent. If we look across from the angle, that's your opposite. And the hypotenuse is the one that is the longest of the three. The hypotenuse in this first equation here, because we have A's and an H here and an O, this equation, the Pythagorean theorem, would be, let's use this triangle, A, B, and C. So each of these could represent the legs here, the hypotenuse for C, and then the angle is always going to be the one we're looking for. We could even look for this angle in a specific problem, but then the adjacent one would be here, the opposite would be pointing across. So whatever angle we're looking for, the adjacent is based on that angle. The opposite is based on that angle. The alternative would be, and in fact that would be the complement of this angle, will point on the other side and flip the equation. So you'd use cosine and sine inversely. Now with this said, I'm going to come up with some numbers, and let's do some calculations with these trig problems. We'll do two. All right, let's solve these two problems. I'm not going to use any units at this point. This is just a strictly math-based problem. And what we're going to do is find the legs A and B here. We're going to find C over here, and we're going to find theta. Now, starting on this side, in order to find A, we cannot use the Pythagorean theorem because we don't have two of the legs of the triangle. So in order to do that, we're going to have to take the 15 and the 20 degrees and use some trig functions. Now, the A is actually the adjacent in this case because it's touching the 20. And what we're going to do is use cosine theta equals adjacent over hypotenuse. So you do cosine 20 degrees equals A over 15. And you cross multiply the cosine 20 and the 15. So 15 times cosine 20, make sure you're in degrees, will get you 14.1. We don't have units. To get B, we need to use the sine. So you would do sine of 20 equals opposite, which is B, over the hypotenuse, which is 15. Also, cross multiply. So you have 15 times the sine of 20, and you end up getting 5.13. So A was 14.1, and B is 5.13. Now, if we want to calculate C on the other side, and theta, what we're going to do is the Pythagorean theorem first. So it's A squared plus B squared equals C squared. 6.5 squared plus 4 squared equals C squared. So 6.5 squared plus 4 squared equals, I have 58.25. But remember, that's the square root. 58.25 equals C squared. Square root of both sides. Take the square root of the answer, and I end up with 7.63. C needs to be bigger than the leg, so that fits. And then finally, to get the angle, I'm going to use tangent. So tan theta equals opposite, points there, over adjacent, which points there. So 4 over 6.5. Now here's what we have to do. Tangent theta equals 4 divided by 6.5. and we get 0.6154, but that's not the angle. The angle needs to be by itself, so you have to bring the tangent over, and you could write it like this, 154 over tangent, but typically what we do is we write tan to the negative 1, and at least that's how it is listed on our calculator, so that's an easy way to remember it. So what you need to do is hit the second function for tangent, and I'm going to, since my answer is still in my calculator, second function and second answer, and I will get 31.61 degrees. So this angle here is 31.6 degrees. So that's how we can find the legs of a right triangle given the hypotenuse and the angle, or find the hypotenuse and the angle given the legs. Pythagorean theorem and SOHCAHTOA are our tools, our mathematical tools in this case.